Have you ever wondered what's really happening when water boils? It's something so ordinary that most of us hardly give it a second thought. You fill a pot, turn on the stove, and within minutes you hear the gentle hiss of bubbles rising and see wisps of steam escaping into the air. But behind this everyday event lies a world of physics so rich and complex that scientists have studied it for centuries. In fact, boiling water is one of the best windows we have into the hidden laws of nature. Welcome to Mattermosaic, where we piece together the universe, one discovery at a time. Today we'll journey deep into the science of boiling water, uncovering why it happens, what it tells us about the universe, and why something as simple as a rolling pot of bubbles has shaped human civilization. If you enjoy exploring the science behind everyday phenomena, make sure to subscribe and stay curious, because today's story will show you how physics lives right in your kitchen. At first glance, boiling seems simple. Heat water until it bubbles. But those bubbles are not just air trapped in the liquid. They are pure water molecules escaping from liquid into gas. What we're witnessing is a phase transition, one of the fundamental processes of matter. Every substance can exist in solid, liquid, and gas states, and the points at which they change depend on two things: temperature and pressure. For water at sea level, the magic number is 100 degrees Celsius, or 212 degrees Fahrenheit. At that exact temperature, the vapor pressure inside the forming bubbles equals the atmospheric pressure pressing down on the surface. That balance is the key that allows bubbles to survive, grow, and rise to the top. To see why this matters, let's imagine boiling water without pressure. If you climbed to the top of Mount Everest, where the air pressure is only about 1/3 of what it is at sea level, water wouldn't boil at 100 degrees Celsius anymore. It would start to bubble at just 70 degrees. At that temperature, your pasta would cook poorly, tea would taste weak, and sterilizing water would be unreliable. On the flip side, in a pressure cooker, where the lid traps steam and raises the pressure, water doesn't boil until about 120 degrees Celsius. That extra heat cooks food faster and kills bacteria more effectively. In other words, boiling isn't just about temperature. It's a delicate balance between heat and pressure, and tweaking either one can change the outcome dramatically. But to really appreciate boiling, we need to shrink down to the molecular scale. Every water molecule is a tiny, V-shaped structure of 2 hydrogen atoms bonded to 1 oxygen atom. In liquid water, these molecules are constantly moving, bumping, and forming fleeting hydrogen bonds with each other. As the pot heats up, the molecules gain more kinetic energy. They vibrate and jostle faster. When enough energy builds, some molecules at the surface escape into the air even before boiling starts. That's why water slowly evaporates at room temperature. But boiling is evaporation turned dramatic. Once the average molecular energy is high enough that vapor can form inside the liquid itself, bubbles appear, and the process accelerates rapidly. The energy needed for this transformation is not small. To raise 1 gram of liquid water by just 1 degree Celsius, you need 1 calorie of heat. But to turn that same gram of water at 100 degrees into steam, you need 540 calories. That hidden energy is called latent heat of vaporization, and it explains why boiling water is so good at transferring energy. Steam carries huge amounts of stored heat, which is why steam burns are so dangerous, and why steam engines powered the Industrial Revolution. Without latent heat, our world would look very different. Storms would behave differently, cooking would change, and many technologies would simply not work. The way heat enters the system is another fascinating layer. At the bottom of the pot, conduction moves energy from the metal into the water. This excites molecules near the surface, which rise upward, while cooler, denser water sinks. This circulation is convection, the rolling motion you can see just before a vigorous boil. As water molecules escape into the air, they carry energy with them as radiation, creating the familiar stream of steam above the pot. Conduction, convection, and radiation are the 3 pillars of heat transfer, and in boiling water they work together seamlessly. It's a laboratory right in your kitchen. But boiling water isn't always predictable. Under certain conditions, you can get superheating, where water heats above its normal boiling point without forming bubbles. This usually happens in very smooth containers, like a clean glass in a microwave, where there are no tiny imperfections for bubbles to nucleate. The liquid sits precariously above its boiling point until the slightest disturbance, a spoon, a grain of sugar, or even a shake, triggers explosive boiling. It is a vivid reminder that boiling is not just about temperature, but also about the microscopic sites where bubbles form. Boiling also links to the history of science. Early civilizations learned to boil water for cooking and safety long before they knew why it worked. In the 17th century, scientists like Evangelista Torricelli and Blaise Pascal explored how air pressure influenced boiling. Their experiments laid the groundwork for modern thermodynamics. In fact, defining the boiling point of water at standard pressure became so important that it was used as a reference in designing the Celsius temperature scale. Today, precision measurements of boiling help calibrate scientific instruments worldwide. Beyond history, boiling water plays a central role in technology. In energy, boiling is the beating heart of power plants. Whether it's coal, natural gas, nuclear fuel, or even concentrated solar, the end goal is usually the same. Boil water, create steam, and spin turbines to generate electricity. More than 80% of the world's electricity still depends on this process. In medicine, boiling was one of humanity's earliest methods of sterilization, and it remains critical in places where advanced equipment is unavailable. In food science, boiling not only cooks but transforms. Proteins denature, starches gelatinize, flavors mix, and safety improves. Without boiling, human diets and survival strategies would look very different. Even in outer space, boiling takes on new forms. In microgravity, bubbles don't rise because there's no buoyant force. Instead, vapor clings to the heating surface, creating unpredictable and sometimes dangerous behavior. Astronauts aboard the International Space Station have studied boiling in detail because understanding it is essential for designing life support systems and cooling technologies in spacecraft. Imagine trying to cool an engine in orbit. If boiling didn't behave the way you expected. The stakes are far higher than a pot of pasta. And here's a mind-bending thought. What if water had a completely different boiling point? Suppose water boiled at room temperature. Rivers and lakes would vanish into vapor, life as we know it would be impossible, and Earth's climate would collapse. On the other hand, if water boiled at 200 degrees Celsius, cooking would be almost impossible without advanced tools, and weather systems would behave very differently. The fact that water boils at 100 degrees under our atmospheric pressure is not just convenient, it is essential for life on Earth. It's a reminder that the ordinary is, in truth, extraordinary. So, the next time you're in the kitchen waiting for a pot to boil, pause for a moment. You're not just watching bubbles and steam. You're witnessing molecular motion, energy transfer, pressure balance, and the deep laws of thermodynamics all working together. A pot of boiling water is as much a piece of physics as the orbit of planets or the birth of stars, only closer, smaller, and easier to see. This is Mattermosaic, piecing together the universe, one discovery at a time. If this journey into the hidden science of boiling water sparked your curiosity, make sure to subscribe for more explorations of the everyday mysteries that shape our world. And when you're ready for your next dive into science, check out our video on how quantum physics shapes our world. If boiling water reveals the laws of heat and pressure, quantum physics takes us to the very foundation of reality itself.